Okay, so in today's lesson, we're going to talk about graphing linear inequalities. Just as a reminder, inequalities can be less than or equal to, greater than or equal to, or greater than. So we're referring to these types of functions instead of the ones that have the equal sign, which is what we've been working on so far. All right, so let's jump on in. So the directions say you're looking to move into a new apartment. You've budgeted $900 a month for rent and utilities combined. Test each of the following combinations below and see if you'd be able to afford that apartment. If you can't afford the apartment, that's important. If you can afford the apartment, bubble in the circle below. For example, you can clearly afford a $400 rent with a utility bill of $100. So this one's already been bubbled in, and you'll see that one right here. So $400 for rent plus $100 for utilities is only $500. So definitely fits within our $900 budget. So what I want you to do now is fill in another circle that you think is possible. Okay, now is there only two possible ways to combine those rent and utility costs? I want you to pause the video again and this time fill in any possible point that adds to less than $900 total. So you should definitely have the first column all filled in, right? Because this represents $100 rent, and this only goes up to $600 possible utility. And you'd have to be using a lot of AC or a lot of water to get to $600 in utilities. But anything in this column is going to add up to less than $900 because it's $100 plus at most $600. So now think about the next column. Okay, again, $200 rent. I can still afford that crazy expensive utility bill of $600 and come in less than $900. Now take a look at the next column. So the only point in this column that I'm not sure about is the very top one. So it says here that I've budgeted $900 a month. And if I pay $300 in rent and $600 in utilities, can I spend exactly $900? I think that's okay since it's our budget max. We just definitely don't want to go over it. Okay, take a look at the next column. Okay, so we're adding $400 for rent. I get up to $500, so that's hitting my maximum amount I'm able to pay on a monthly basis. So that means I cannot fill in this point at the very top because $600 plus $400 is going to give me $1,000, and that's over my budget. So let's see if the same thing is going to happen in this column here, which would be for $500. Okay, I know I'm going to be good there. We're good. I'm getting to 900 here because we've got 500 plus 400. This represents 450. So that's going to put me over 900 total. And then anything else above that will also be above my budget. So I want you to go through the remaining columns and do the same process and see how far up can we actually afford that amount of rent with any combination of utilities. Okay, so see if yours looks the same as mine. For $600, I could go all the way up to $300 in utilities. For $700 rent, only $200 in utilities. And then for $800 rent, I can only afford $100 in utilities. That means by the time I get to this next column, that represents, right, this was 700, this represents 900. So I can't actually afford an exact rent of 900 because then I can't afford my utility bills. And that, again, is just like your electric, your gas, your water, city trash, anything of that nature. All right, so these are all the possibilities, right? Well, let's take a look at the extension question. It says, do values in between the circles also work? Because right now we're only focusing on the specific whole increment coordinate points, like in hundreds. In other words, could you afford an apartment with a monthly rent of $550 and a utility bill of $100? Well, let's look for where that would be. So $550 rent would fall somewhere around here. And a utility bill of $100, that would take me right there. So is that less than $900 altogether? Yeah, that only brings us what, to $650? So that means that it's not just the pretty numbers, right, the hundreds, it could be the numbers in between these as well. In fact, most of your bills and rent might be in hundreds, but your bills usually are in even amounts. So it's not just that all these points that we filled in are possible, it's everything between them, right? So anything between them, and not just in this column, right? Obviously for things less than that, we'd be okay as well. And maybe up to at a certain point. Like there's some sort of boundary occurring here, and I don't know exactly where it is, but it's there. So I'm going to kind of fill in what I know I can afford, and you can do this very lightly with your pencil or you're going to use all your lead. So just lightly fill in all the spaces between your points as well, because it doesn't have to be whole increment amounts. Okay, I think we're good on most of this. You might have to start thinking a little bit harder here. Okay, so I can see that there's some sort of kind of like invisible border, but I don't know how far up to color some of these, right? Because these don't go all the way to the top. So where's this boundary here? So what we're doing is we're graphing the line 900 equals x plus y, where x is your rent and y is your cost and utility bills. So basically we need to find a way to kind of graph this above and see if this helps us out. So let's think about the shading a little bit more. So like if I had something like 350, right? I could afford all the way, let's see, 900 minus 350 would be 550. So I could fit maybe up to the halfway point here on that shading. And then here, 450 plus 450, yeah, that's exactly half. So about halfway up this one. And then maybe 550, I can go up to 350. And then 650 can go up to 250. And 750 can go up to about 150. And then 800 could go up to 50. Something like that. All right. So if we try to graph the line x plus y equals 900, right, we know that 500 plus 400 would be on there. And we know that that was 400 plus 500. This is 500 plus 400. 600 plus 300. 100, wow, I can't read my own handwriting. 700 plus 200, 800 plus 100, and then 0 if we spent all our money on rent. Okay, and so we should be getting something along this line. Let's see, 300 and 600. You know what? Miss Wright made a mistake here. This is not 600. I hope some of y'all noticed that when I made that mistake. These are going up 2 squares per 100. So that square is really 550, right? So I need to be careful with that. So that means 600 is really at the tippy top. So 300, 600 would really be way up there. Okay, so now I'm going to try to connect these to graph my line 900 equals x plus y. And I want you to look at where we've shaded our possible combinations and where this line is falling, right? I want you to take a second and write a sentence about what you can see about where that line falls and where our solutions are located on the graph. All right, so there's lots of ways to say this, but one way that makes the most sense to me is I think of it like a boundary line. Right? Our solutions can go up to it, but not past it. So I think of it as the boundary line of our solutions. Okay. It's also, basically all the shading is contained below it, right? And to you guys, it's going to look like to the left, but in reality, these are values below the line or less than $900 when we combine them. Okay. So the shading is only below. Awesome. Let's turn the page. Okay, so now take a second to think, why did we shade one side of the line in the previous page but not the other? So looking back at this picture, how come we didn't pick any of the points over here to shade in? Well, if we take a look at them, right, this is a rent of $1,000. I can't afford that. And while this represents the rent value of $600, my utilities are $500, and together that's over $1,000. I can't afford that either. So the reason we didn't shade anything on the other side of the line is because we couldn't actually afford it, right? So basically the side we shaded contained combinations we could actually afford, like $400 rent and $400 utility. But the other side did not contain combinations that would work for us. Okay, so let's try some other examples. So it says graph the following 3 inequalities on the coordinate planes below. So here are your inequalities down here, and remember this particular sign is called greater than or equal to. So we're looking at combinations of x and y points, where when we add the two values together, it's greater than or equal to 5, and they have this in words right down here. All points whose x and y values add up to 5 or more. So let's start at 0. Is there any number that when I add it with 0, it's greater than or equal to 5? Well, the best and closest one would be 5 itself, right? Because 0 plus 5 is at least equal to 5. And then, of course, anything above that would also work, right? Anything, actually, we'll do some shading in a second. That's the minimum we would be able to do. Okay, so anything above that would also be okay. Let's look at 1. What can I combine with 1 that is 5 or greater? Well, 4 is the smallest it could be, and then it could be anything above that. All right, let's see. 2 plus 3 is at least 5, and then anything above that would be greater than. And then same with 3 and 2 going the other way. That's about the same idea. Then we have 4 with 1 again, and 5 with 0 again. So those are the minimums just to get it to add to 5. So then anything else above it would also work even better. They would definitely be greater than. And so we're going to fill in a line or a boundary line that's occurring between our solution, our feasible solution region, and our non-solutions, or numbers that when I combine this coordinates x and y is not 5 or greater. All right, take a look at the second one. It says x is greater than or equal to y. The x values are greater than or equal to y. So for the x values to be greater than y, that means that we could have points like 1, 0, or we could have points like 2, 0, or 3, 0, because those are all values where the x coordinate's bigger than the y coordinate. But what about 0, 0 itself, right? Well, since this has an equal part to it, 0 can equal itself, so we could also include the point 0, 0 to start with. All right, so that's basically that whole bottom row. What about going up the side, right? These are points like 0, 1, 0, 2, 0, 3, and so on. In this case, are the x values greater than or equal to the y values? Well, every single point going up this column is going to have an x of 0, which is definitely not greater than these y values. So we're not actually going to fill in any of these. So let's take a look at the next column here, starting with 1, 1. Those are when they're the same, so that works. If I go to 1, 2, well, 1's not bigger than 2, so I can't use that one. Let's try 2, 1. 2, 1 should be okay because 2 is bigger than 1. Okay, what about 2, 2? Oh, well, if they're the same, then that equal part helps me out. We're good with that. What about 2, 3? That one's not working. We gotta take that one away. All right, 3, 1 is definitely good. 3, 2 is definitely good. 3, 3, yep, the ones that are equal to we're definitely okay with. And then 3, 4, actually no, that's not going to work because 4 is not smaller than 3. So now we're going to move to the next one. 4, 1 I know works. 4, 2 I know works. 4, 3 sounds good. 4, 4 we know is okay. But then when we get to 4, 5, that y value is not smaller anymore. So we're going to stop there. And what I want you guys to start looking for is, where is the cutoff point, right? So where is it no longer working? And it seems like after 1, 1, 2, 2, 3, 3, 4, 4, we can kind of think of it just going along this particular boundary line. Because after they're equal, then the y value becomes bigger if we keep going up. So in reality, if we're shading our solutions, anything below this boundary means we're good. Those combinations have x values that are larger than the y values they're at. And that's how we would notate that it could be any combination, right? There's a bunch of decimals in here I'm kind of overlooking. I just use test points that are easy, so I stick with whole numbers. But the decimals work too. All right, here we have y less than or equal to 4. So it's all the points whose y values are less than or equal to 4. So think about the point 0, 0. That definitely has a y value less than 4. 0, 1 works. 0, 2, 0, 3. 0, 4 is that equal part, which means we can't go above to 5 because then that y value is too big. Okay, so 1, 0, 1, 1, 1, 2, 1, 3. 1, 4 is equal to, but 1, 5, that's not going to be less than or equal to 4 anymore for our y values. And then we just keep looking, and when we go to an x of 2, it's the same thing, right? So what you notice here is it's really only the y values that we care about. Whether I go left or right on here isn't affecting where my boundary line is falling. Okay? So in each of these, by the time I get to a height of 4, my y values are going to be bigger after that, so I have to stop. So that seems to be my boundary line, and what I want you to see is this is exactly how we would graph y equals 4, right? The only thing that's different with the less than or equal to means that we include everything not just on the line as a solution, but also anything that makes this inequality true. So if it's less than or below the line, or exactly on the line, then we're good to go. All right, let's keep rocking and rolling. It says, fill in the circles that complete each of the following inequalities. So now we're looking at x, right? Where are the x values of the coordinate points greater than or equal to 3? So you're looking at these numbers here. So obviously anything greater than is good to go. So an x value of 4, these have an x value of 5, and these have an x value of 6. What about 3 exactly? Well, this has an equal part to it. So we're going to also include all the points that have an x value of 3. Now, if I go to an x value of 2, that's no longer greater than or equal to 3. So we're not going to go past that boundary. It seems like our cutoff, our cutoff boundary is this vertical line, which again makes sense because that's how we're used to graphing x equals 3, right? It's just that now we have shading that everything on the right side of that would also have that quality. And that's what's making it greater than or equal to 3 versus regular equal to 3. Now when we look at the one next to it, it's almost the exact same with one small difference, right? What's different about this one? Right, the little equal part is no longer there. So I can definitely still have x values of 4, because that's bigger than 3. I can have x values of 5, because now anything over 4, of course, is also over 3. So all of these still work. But 3 greater than 3? No. Okay? 3 can't be greater than itself. It can be equal to, but not greater than. Which means that unlike this graph where we had the ones in 3 filled in, we can only go up to 4. Or to any decimal really close to 3, right? So like 3.1 is greater than 3. 3.01 all the way up to it, right? So if we kept thinking about decimal answers, we could really fill in any of the space that's right up to that line, just not exactly on it. Okay? Not exactly on it, but right up to it. Oh, too far. Okay. And the way that we notate that it can't be exactly the line but can come straight up to it is to have a dotted line at the border instead of a solid one. That tells us, hey, you can be anything right up to the very edge of this, but you can't actually be equal to it like we could in the first one. So now I want you to take a second and summarize the difference between these two on these lines here. The main thing we want you to take away from this is that when you see the equal part as part of the solution, you should have a solid line on your graph. And when you see the dotted part as part of your solution, that means you don't have the equal part in your algebraic expression. You just have a greater than or a less than. All right, last page. So it says graph each of the following linear quantities. Use a dashed, sometimes we call it dotted, line to show the boundary of the shaded area when points on the boundary do not satisfy the inequality. Okay, so this one says y value is greater than twice the x value. So let's start with x, multiply it by 2, and see where that takes us. So if we started an x of 1, twice that would take us up to 2. If we start with an x of 2, twice that would take me to 4. An x of 3, twice that would take me to 6. So that's going to be where our boundary is located, okay, because we found the y values that are twice as big as the x values of that coordinate. The question is it a solid line or not, right? And since it doesn't include it, it's not got the equal part, we use a dashed line. And you're just going to do the best you can on this. It's not going to be perfect. A dashed line. Now, if this is the boundary and we're looking for anything else that's possibly greater than that, I want you to start thinking of greater than as shading up. Shade above your boundary. So above means if you put your pencil on the boundary and drug it up, it's going to be that side of the line. So in this particular case, it's going to be everything above it is also part of the solution, just not exactly on it. Okay, let's try the next one. This one says all points whose x value is more than 2 higher than the y value. Okay, so let's start with an x of 1. More than 2 higher than the y value. That's going to be hard to do because 1's not very big. All right, what about 2? Okay, well, if x is 2, the only way it can be greater than, right, would be if y is 0. So that would be something on the boundary. If x is 3, 2 greater than 1 is what we're looking for. If x is 4, that's 2 greater than 2. If x is 5, that's 2 greater than 3. And you can see we're starting to get this nice diagonal pattern here. If x is 6, that's 2 greater than 4, so 6, 4. And if x is 7, I think it's just going to keep going diagonally. Okay, so those are the ones that are exactly on that boundary. However, we can't have those, right? Because it said had to be greater than, not greater than or equal to. So we're going to have a dotted line. And then anything past this, we should be okay with, right? So like, let's just use the test point 5, 1 and make sure. So that has an x value of 5 and a y value of 1, which means I'd have 5 is greater than 3. Is that true? Yeah. So that means we're going to shade everything on that side. You could also go the other way and test something on the other side and make sure it doesn't work, right? So if I looked at the point 2, 5, that has an x value of 2 and a y value of 5. Is 2 greater than 7? No. So you would not want to shade that side because that's not a true statement. All right, and the last one, all points whose y value is less than 4. Okay, so let's look at our y's over here. Okay, I want the ones that are less than 4. So it could be right up to, but not including, like 3.999. It just couldn't be 4 exactly. So 4 is where this boundary line is going to be occurring. We definitely can't go past it. And since it doesn't have an equal part on it, we can't actually equal it either. So we're going to make a dotted line here going across. And it could be any y value less than that as well. So like if we look at this point here, the y value there is 2, and that's definitely less than 4. So we can shade anything that's falling below. So a lot of times if you have the y by itself, there's a nice trick with shading. If you have y by itself and it says y is greater than, you're going to shade above. If you have y by itself and it says less than, you're going to shade below. It gets harder when y is not by itself. And for those, a lot of times I just pick a point, I plug it in, and see if it gives me something true or false. If it's true, I shade the side that point is on. If it's false, I do not shade that side.